Hi. Today we're going to talk about distributive lattices, which have a lot of really cool properties. So let's start by recalling what a modular lattice is. Okay, lattice L is modular if for any x, y, and z in L such that x is less than or equal to z, then the following holds: x join y meet z is equal to x join y meet z. Okay? So a non-example, a non-modular lattice, is the lattice that is sometimes called N5 in the literature, and it looks like this. Okay, we have x less than or equal to z, and y over here. This is our 0 element, and this is our 1 element. Okay, so it satisfies the requirement that we set x is less than or equal to z, and if we take x join y meet z, that's x join 0, which is just x, whereas if we take x join y meet z, that's equal to, well, x join y is 1, and 1 meet z is z. So clearly these two things are not equal, which means that the lattice is not modular. But we can say something even stronger. A lattice L is modular if and only if it does not contain N5 as a sublattice. And the proof, well, going in one direction is relatively easy. So clearly if you have a modular lattice, you can't have this as a sublattice because that would present contradiction of modularity. Okay, so this is C, the non-example. In the other direction, it's much trickier, but if you have some the way we would prove the contrapositive. So we would say if the lattice is not modular, so assume L not modular, then we have to produce N5 as a sublattice. And the way you would do that is by saying, well, first you have to have some x, y, and z that contradict the defining condition. There exists x, y, z with x less than or equal to z, such that x join y meet z is not equal to x join y meet z. Okay? So once you specify that, which is just a consequence, it's equivalent to the idea of not being modular, then you will be able to find the following sublattice. L contains, and on top here we're going to have x join y. Here we'll have y. Here we're not going to have z, we're going to take x join y meet z. This will be x, and then down here we'll have x meet y. Okay? And in order to prove that this is actually a sublattice, you have to show that all of these covering relations hold, or I guess just inequalities hold, strict inequalities, and also that these two pairs of elements are incomparable. Okay? So the details of the proof are omitted. But that's how you would show that this lattice is in there. Okay. Now let's talk about distributive lattices. Okay. A lattice L is distributive if for all x, y, and z we have the following in L, x join y meet z equals x join y meet x join z, and also x meet y join z. And technically these are equivalent, so you don't really need to have both, but for the sake of completeness, or for the sake of symmetry, I suppose, x meet y join x meet z. X meet y join x meet z. Okay. So a non-example for this property would be if you take the lattice often called M5 in the literature, and that's given by 3 incomparable elements with a 0 and a 1. This is our x, y, and z. This is our 0 and 1. Then it's not too hard to see that if you have x join y meet z, then you're going to have y meet z is 0, so x join 0 is x, whereas x join y meet x join z is, well, this is 1 and this is 1, so it's just 1. Okay? So that shows that this is not distributive, since these two things are not equal. Okay, but you will notice that M5 is modular. Okay, and you can check that on your own just by taking any sets of elements where x is less than or equal to z, and the remaining one is perhaps incomparable. The relationship between distributivity and modularity can be summarized as follows. Okay, distributive lattices are modular. Okay, and the proof of that is rather simple. So in the distributivity law, if we take x less than or equal to z, then x join y meet z equals x join y meet x join z. Well, x is less than or equal to z, so this is just z. So this is x join y meet z, and that's exactly the modularity condition. Okay. So what's interesting is that this modularity property, together with this non-example, is enough to characterize distributive lattices. So if we take So we can say that a lattice L is distributive if and only if it does not contain N5 or M5 as sublattices. Okay. So not containing N5, that's a property of modularity. That's the defining characteristic of modularity. Not containing M5 is for those distributive lattices that are modular. Okay? So those modular lattices that are not distributive. So once you rule out both of those cases, you can be certain that your lattice is distributive. And to do a quick proof, okay, so clearly, just as before, going in one direction is easy, so, okay, see the non-examples. Going the other direction is tricky. Okay, so so let's assume it's not distributive. So there are two cases. Either it's not modular, so it's both not modular and not distributive. Okay, so not modular. So this is case one. Then it contains N5, okay, by the above. Case two is that it's modular but not distributive. Okay. Then you're able to produce a contradiction to the distributive law. So you can take, for example, there will exist x, y, and z in L such that x join y meet z is not equal to x join y meet x join z. And once you get those three elements, using these three elements, we can show that the following three elements are incomparable, but any pair of them has the same meet and join. So, or we can show L has the following sublattice. Then we'll put in, so it's going to look a little messy. X meet y join z, join y meet z. And here we have the same thing but with y at the beginning. I'm just permuting the labels. Y meet x join z, join x meet z. And over here we'll have z meet x join y, join x meet y. Apologies for the messiness. And you can show that all three of these have the same pairwise meet and the same pairwise join. switch order of those words. So this is the searched for sublattice. Okay, and this is isomorphic to M5. Okay, obviously there's a lot that goes into that proof. I'm going to give a link to an argument about this in the notes to the video. Okay, but it's really interesting that both of these very important lattice properties, modularity and distributivity, can be characterized by just these two forbidden sublattices. Okay. So we'll see the definitive way to construct examples of distributive lattices is to take the lattice of order ideals. So let's recall what an order ideal is. Order ideal I, which is a subset of our poset P, is a subset such that for any x in I, if z is less than or equal to x, then z is also an I. Okay, so it's closed downwards. Anything that's below an element in your order ideal is also in your order ideal. Okay, so there's a lattice that results from taking the set of all order ideals in your poset. So J of P equals the lattice of order ideals of P where the ordering is given simply as I1 less than or equal to I2 if one is a subset of the other. Okay, it's very simple, simple ordering. Perhaps we should do a quick example. So if we take, let's take P equal to this together with this. Okay, it's arbitrary poset. It's a disjoint union of two smaller posets. Okay, so we have A, B, C, D, E. Okay, so with this, there are a number of there's a lot of order ideals here. Perhaps I should have picked a smaller example, but let's work with it. So we could take any of A, B, and C on their own. First of all, we can take the empty order ideal. Okay, so this is our 0, the empty order ideal. We could also take any of A, B, and C on their own. Okay. We could also take A and B together because those two elements are minimal. None of the other elements of the poset are above them. Could also take and notice that this order ideal is a subset of that order ideal. Could also take AC. Could also take BC. And we could also take all three of them. Okay. Once we have A and B, though, we could also put in D. So let's put D over here. This will be A, B, D. Okay. And we could have A, B, C, and D. Okay. Once we have C, we could also have E. So that'll be CE. And then we could put A together with that, or B together with that. So that'll be ACE, and this one will be BCE. Okay, and then over here we can get A, B, C, E, and then taking the join of these two, we have the full set A, B, C, D, E. Okay. So it's a lot of order ideals here, but you can notice a lot of things just from this example. For instance, you can put the rank function very simply as the number of elements in the order ideal, right? This is 0, this is 1, 2, 3, 4, 5. Okay? And you'll have distributivity from properties of taking unions and intersections of subsets. And you have a lot of nice local structure here. It looks a little bit like a Boolean lattice in a lot of places. But this is an example of JFP. So it's a lot more complicated than just P. Okay, but the reason that order ideals and the lattice of order ideals is so important is the following theorem, which is sometimes called the fundamental theorem of finite distributive lattices, which I'm sure you've all heard of because it's fundamental. This is FTFDL, and the theorem says that so every distributive lattice L has a subposet P such that L is isomorphic to J of P. Okay? So this is a big deal. This characterizes, sorry, this should say finite. That's part of the name of the theorem. So this characterizes all finite distributive lattices in terms of this really basic construction of the lattice of order ideals. Okay, so what goes into proving this? Well, here's how the proof goes. We define a property of elements in a lattice called joint irreducibility. Okay, so an element S in L is joint irreducible if there are no two elements T and U not equal to S such that S equals T join U. Okay. Then if we take P to be the subset of elements of L, P equals S in L such that S is join irreducible, then L is equal to J of P. And the key to proving that is you take some element in L, so take T in L, and we can map this to what we call lambda T in J of P, which is defined as lambda T equals the set of elements S in P such that S is less than or equal to T as elements of L. Okay, so that's clearly an order ideal because it's closed under this less than. And our claim is that every order ideal corresponds to a principal order ideal defined in this way. So we claim that this map is a bijection. Okay, so we have to prove that. So take I or let's make it in the set of order ideals of P. Then we will show that it corresponds to some specific, okay, we're going to show that I equals lambda T for T equal to the join of all of the elements S I, where you have to take the join in terms of the lattice. Posets don't have a join operation, but taking the join in the lattice of all of the elements S that are in that order ideal. Sorry, I had to relocate, but picking up where we left off. So we're going to show that I equals lambda T for T equal to the join of all of the elements in I. Okay? So clearly, well, if T is above all of the elements in I, then I is certainly contained in IT. That part is easy. The difficult part would be is to show that IT is contained in I. So we're going to take, so we're going to suppose not, so take U in I, or in IT I should say, not in I. Okay, so this is an element in P, which is in the principal ideal generated by T, meaning it's below T, but it's not among the elements that were in I to begin with. So the fact that T is the join of all of the elements in I means that the join of all of the elements S in I is equal to the join of all the elements S in IT. Okay? And that's just because T is, I mean, clearly T is the result here, but T must also be the result here. Okay, these are just both equal. So what we're going to do next is we're going to take the meet with U. This is also T. We're going to take the meet with U. So this implies the join of S and I meet with U equals the join of S and IT meet with U. Okay. So we know that U is in IT. So by distributivity, we have that we can put this inside here. Okay, that's by distributivity. And we know that one of those S's is U because U is in IT. So this must be U. Okay, because everything else is at most U, and one of them is exactly U, so taking the join, it must be U. Okay. Looking at the left-hand side, so we apply distributivity. Meet with U, S is in I. So by the fact that we have that this is equal to the right-hand side, we must have that this join is equal to U. But U is join irreducible since it's in P. So one of these elements must be U. And that implies that U is in I. Okay, which contradicts our previous assumption. I guess it didn't really need to be framed as contradiction. You could use this argument to show that IT is contained in I. Okay, so that's really the main part of the proof of the fact that a lattice is the lattice of order ideals of a subposet. And there are some details that can be filled in from Stanley, but let's move on to an illustrative example. So let's take the lattice given by this square. This is a distributive lattice. So in order to extract the subposet whose lattice of order ideals is given by this, I look for the join irreducible elements. Okay, so 0 is excluded from that. So this element is join irreducible, as is this. It's not the join of anything. This and this are also joint irreducible. This is the joint of these two, this is the joint of these two, this is the joint of these two, and this is the joint of these two. So these are enough. So extracting that poset, I'll get that this is the lattice of order ideals of two chains. Okay? And if I if I wanted to read that back in, it would be as simple as following. So this is the empty order ideal. This is the order ideal containing just A. It's the order ideal containing just C. Order ideal containing AB. The order ideal containing CD. This is the order ideal of AC. This is ACD. This is ABC, and this is ABCD. Okay? So that's how you can show that starting with a lattice, you can go to its sub-poset of joint irreducibles, and then go back via JFP. Okay? Some lattices of order ideals for kind of classic posets. If I take the join of the chain, the lattice order ideals of the chain n, what I'll get is the chain n plus 1. Right, because you have an order ideal corresponding to each element in the chain, and then also the empty order ideal. Okay. Additionally, if I have n copies of 1, i.e. an anti-chain of size n, the lattice of order ideal is the Boolean lattice on n elements, because you have, think of each of those elements in the anti-chain as atoms of the lattice, and then you can take joins freely. Okay? So this is actually quite useful when you're trying to draw a Hasse diagram of JFP for some arbitrary poset. Let's show an example doing that. The example that I think Stanley uses is this large zigzag. I'll use a slightly smaller zigzag because I don't want to do as much work. So if we have this poset, this is our P, we label the elements A, B, C, D, E, then the first thing that we can do is we can look at all of the minimal elements. Okay, so the minimal elements form an anti-chain, and so the corresponding lattice of order ideals among those minimal elements is a Boolean lattice. Okay, so we can start by just taking the empty order ideal and then taking the Boolean lattice on 3 elements. Oops, this is not correct. So we can take our poset to be this one. Okay, it's sometimes called a zigzag. It's a bit smaller than the example in Stanley, but we have 3 minimal elements here. So the 3 minimal elements, if I just focus on those, that's an anti-chain of size 3. This is representing a chain of size 1. So j of 3 times n, but 3 times 1 by what we just said is the Boolean lattice on 3 elements. So we can start by building the Boolean lattice on 3 elements. Okay, so we start with the empty order ideal, and then we have the order ideal just containing A, B, and C. Building up to the next level, this will be AB, which contains the order ideals of A and B. Over here we can put AC, and here we can put BC. Okay, and then above them all, I'll have ABC. Okay, so that's the Boolean lattice that we obtained just focusing on the minimal elements. Now the next thing that we do is we look at any minimal element of what's left. Okay, so both D and E are minimal in the remaining elements. So I want to put D into this lattice. I want to figure out where to add it in. And I see, well, D is above A and B. So I want to look at the join of both A and B and put D above that. Okay, so D will be here, correspond to the order, the order ideal ABD. Okay, and I'll want to take joins with anything else above AB. Okay, so that is just ABC at this point. Okay, and now I have one more element excluded, and that's E, and that's got to be positioned above BC. So E will go here. Okay, we also want to take joins of anything above BC. Let me specify that this is BCE. So I'll put this guy here. So this one was ABCD, and this is ABCE. And I'll take the join of these two to get ABCDE. Okay. And this is the lattice of order ideals for this. And you can, given any poset, you can construct the lattice of order ideals this way. Start with the minimal elements, and then build up an element at a time, filling in any joins that are missing. Okay, there are just a couple more results that I wanted to discuss in this lecture, and they involve multi-chains and chains in order ideals, in lattice distributive lattices, or the lattice of order ideals. So we have P, a finite poset, and M, a positive integer. Then the following are equal. So the number of order-preserving maps sigma from P to M, where that's the chain on M elements. This is equal to number of multi-chains and we're going to take the empty order ideal as I0, and this will be less than or equal to I1 up to IM, which will be the join of all of the elements, the maximal element of the distributive lattice. And these are all multi-chains in J of P. And this is equal to the number of elements in the lattice of order ideals of P direct product with the chain M. Sorry, chain M minus 1. Okay. So, this is a pretty cool idea, and I'm just going to sketch the proof. So if we start with an order-preserving map sigma from P to M, then you can use that to construct a multi-chain of order ideals. Ij is equal to the set, or is equal to the preimage of under sigma of the chain J, i.e. sigma inverse of 1 through J. We seem to be having some video recording difficulties, so my apologies for that. But we were in the middle of discussing the idea of the proof of this equation of order-preserving maps, multi-chains, and this order ideal, this lattice of order ideals. The idea of the proof is basically to start with a function, an order-preserving map from P to M, and then you send it to a multi-chain of ideals where each ij is just the preimage of the chain 1 through j under the map sigma. Okay, and then we just need that to map to an order ideal of P cross M minus 1. And the way that that happens is that you send it to the order ideal given by the set of T and J. Okay, this is an ordered pair where T is in P and J is in M minus 1. And the way that these two get paired up is if T is in I sub M minus J. Okay? And then the way you go from here to an order-preserving map is you take sigma of T for T in the poset P. Sigma of T will be given by the smallest value of M minus J for Tj in I. Okay, where i.e. J is varying over all pairs Tj and I. Okay, so we're not going to go too rigorously through a proof of this, but we'll look at an example and see how it plays out in an example. So let's say we're working with the poset P equals this little diamond. Okay. And then we'll let the integer that we're interested in be 3. Okay? So we claim that the number of order-preserving maps from this poset to the chain 3 will be equal to the number of multi-chains of length 3 in the order ideal of P, in the lattice of order ideals of P, and that it will be the same as the number of elements in the lattice of order ideals of P cross M minus 1. Okay, so let's start with a specific map from P to the chain 3. Okay, that'll be the chain 3. And we'll just denote it by listing the values. We'll say this will be 1, this will be 1, this will be 2, and that will be 3. Okay, so that's a function. It's order preserving because whenever you have you have two elements of the poset where one is less than the other, then the values are also less than or equal to. So to go from there to a multi-chain of order ideals in P, so first let's draw what. So in order to do that, we'll take, so I0 is just the here, let me draw this over here. So I0 is just the empty ideal. I1 is equal to the preimage of 1 in the poset, which is just this lower two elements here. So it's given by that as a subset of this poset. So it's this order ideal. And then I2 will be the preimage of the chain from 1 to 2, which will just be the preimage of 1 and the preimage of 2 together. So it's this. And then I3 will be the preimage of the chain up to 3, which is just the whole poset. Okay. In terms of the order ideals of P cross M minus 1, okay, so this was the order preserving map. This was a multi-chain of order ideals. It happens to be a chain also because each one is properly contained in the next, but you could have had, let's say if 2 wasn't valid, if this was also 1, then we would have had this one being the bottom 3 and then this one also being the bottom 3, which would be a multi-chain. So to go from this multi-chain of order ideals to the order ideals of the direct product, so we're going to list Tj such that T is in I sub 3 minus j. Okay? So if we label the elements of this poset A, B, C, D, then we have this set will contain, well, A is in I1, I2, and I3, so we'll have, oh, and this is J and M minus 1, so we'll have A1 and A2. Okay, you don't have A0 because 0 is not in this chain. B is in I1, I2, and I3 also, so it'll be B1, B2. And C is just in I2, not I1, so that's C1. And D is only in I3, so we don't list any elements with D. Okay? And we can check that this is an order ideal in this direct product. In many ways, one way to do it would just be to draw out the direct product. So recall that we can kind of draw a copy of one of the lattices inside of each vertex of the other one. So we have a 2 chain, and we'll draw it at each vertex of the diamond. Okay. Okay, so you might notice this is actually a Boolean lattice, which is nice. But what do these represent? Well, this is A1, this is B1, C1, and up here is D1. And then this next diamond is just all the same, but with A2, C2, oops, C2, B2, D2. The order ideal that we just specified is A1, A2, B1, B2, and C1. And you can see for yourself that's clearly an order ideal. Okay, and now to get the order preserving map, that this is meant to specify. So we can go if we wanted to go up in this direction again, we would say, well, what's the smallest value for each element here? What's the smallest value of m minus j? Okay, well, for A, so sigma of A equals the minimum of 3 minus 1 and 3 minus 2, which is 1, 2, so it's just 1. Sigma of B is the minimum of also 1 and 2. Sigma of C is the minimum of just 3 minus 1, so just 2, and that's 2. And sigma of D, because it doesn't appear, you just say it's minimum of 3 minus 0, which is just 3. And that's exactly the map that we were describing. Okay, so that's roughly how this proof goes down. And just some slight observation helps to introduce a slight variation of that theorem to say that the number of surjective order preserving maps from P to the chain M is equal to the number of proper chains, not multi-chains. So at every step you're strictly increasing, where you start with the empty ideal and you go strictly up the chain to IM, which is the full ideal of length m. And the explanation of this is straight from the last same bijection as above, but instead of allowing arbitrary functions from P to M, you require them to be surjective, which means that as you go up your chain, you pick up new elements whose value is the new integer. Slight variation. Okay, I think we'll end there. Thank you. And apologies for the technical difficulties.